What if everything we thought we knew about the universe was just the tip of the cosmic iceberg? Picture this. You're staring up at the night sky, marveling at the vastness of space, convinced that the rules governing its expansion are set in stone. But what if those rules aren't as fixed as they seem? Hidden in the fabric of the cosmos are whispers of events so bizarre, so utterly unexpected, they threaten to upend our entire understanding of how the universe grows and evolves. These aren't just minor glitches in the cosmic code, they're universe-bending anomalies that defy explanation, and they've been lurking in the shadows all along. For decades, scientists believed the story of cosmic expansion was a straightforward tale of galaxies drifting apart, driven by dark energy and the echoes of the Big Bang. But then came the anomalies, gravitational ripples that shouldn't exist, bursts of energy with no clear source, regions of space where the laws of physics seem to twist and warp. These aren't just curiosities, they're clues pointing to a far more complex and mysterious universe than we ever imagined. And the most startling part: there are 28 of these forgotten events, each one a piece of a puzzle that could rewrite the story of everything. This isn't just about science, it's about the very nature of reality itself. What if the universe isn't expanding the way we thought? What if there are forces at work beyond our current comprehension, bending the fabric of space-time in ways we're only beginning to glimpse? Today, we're going on a journey through these 28 cosmic enigmas, uncovering the secrets they hold and exploring how they challenge the foundations of modern astrophysics. By the time we're done, you'll see the night sky in a whole new light, not as a static backdrop, but as a dynamic, ever-changing tapestry of mysteries waiting to be solved. So buckle up, because the universe is about to get a lot stranger. The first forgotten event that shakes our cosmic understanding begins with a ghostly encounter, two galaxies that seemed to collide and then vanished without a trace. Astronomers call it the Phantom Galaxy Collision, an event that left behind gravitational ripples and fleeting light signals, but none of the cosmic wreckage we'd expect. When galaxies merge, they usually leave behind a trail of stars, gas, and dust, like celestial breadcrumbs marking their violent dance. But in this case, the universe gave us the aftermath without the mess. It's as if someone hit the cosmic reset button, erasing all evidence of the collision. What makes this even stranger is that our current models of galactic mergers can't explain it. Every simulation, every equation predicts debris stellar shrapnel scattered across space. Yet here, the universe seems to have broken its own rules. Some scientists speculate that dark matter, the invisible scaffolding of the cosmos, might have played a role. Could it have somehow swept away the remnants like a cosmic broom cleaning up after the collision? Others wonder if an entirely unknown force was at work, something beyond our current physics. This phantom event forces us to reconsider the life cycle of galaxies. If mergers can happen without leaving a trace, what else have we missed in the grand story of cosmic evolution? It's a humbling reminder that the universe still holds secrets we haven't even begun to unravel. And if something as fundamental as galaxy collisions can defy our expectations, what other surprises are waiting in the depths of space? Just when astronomers thought they'd seen it all, the universe delivered another curveball, the Great Void Eruption. Picture this, a seemingly empty patch of space, dark and unremarkable, suddenly lighting up with a burst of radiation so intense it dwarfed entire galaxies. This wasn't just another cosmic flare or a distant supernova. The energy signature was completely alien, defying every known classification in the astrophysical playbook. It was like hearing a note no instrument on Earth could produce, a cosmic scream from the void. What makes this eruption so baffling is its location. Voids are supposed to be the deserts of the universe, vast regions where matter is scarce and activity is minimal. Yet here, in one of these cosmic dead zones, something erupted with enough force to rewrite the rules. The leading theories sound like they are pulled from science fiction. One camp suggests this could have been a collision between parallel universes, a fleeting moment where the fabric of reality brushed against another dimension. Others argue it might be evidence of quantum decay, where the very vacuum of space itself briefly destabilized, releasing unimaginable energy. Then there's the timing. Unlike predictable cosmic events, this eruption left no warning. It flared into existence and vanished just as quickly, leaving behind only a whisper of radiation as its calling card. If not for sensitive telescopes catching the afterglow, we might never have known it happened at all. That fleeting nature raises even more questions. Was this a one-time cosmic glitch, or are voids far more active than we realize? Could there be an entire hidden layer of universe-bending events happening in the emptiest places imaginable? The implications ripple through astrophysics. If voids can produce such violent eruptions, our maps of cosmic energy need serious revision. It challenges the very definition of empty space, suggesting that even the darkest corners of the universe might be teeming with unseen activity. Perhaps most unsettling is the realization that if an event this colossal could go unnoticed until recently, what other universe-altering phenomena are happening right now, just beyond the edge of our detection? The Great Void Eruption isn't just a mystery, it's a wake-up call that the cosmos still holds realms of unpredictability we're only beginning to sense. The universe seemed to press pause on one of its most violent spectacles when astronomers witnessed the Time-Dilated Supernova, a stellar explosion that defied all expectations by unfolding in extreme slow motion. Normally, a supernova races through its death throes in mere weeks, a brilliant flash of cosmic rebirth. But this one stretched across centuries, its light curving and dimming as if trapped in some invisible cosmic syrup. It wasn't just a delayed show, it was as though time itself had fractured around the dying star. What could bend time so dramatically? Einstein's theories tell us massive objects warp space-time, but this was something far more extreme. Imagine tossing a pebble into a pond and watching the ripples crawl outward at the speed of honey. That's how aberrant this event appeared. Some researchers point to the possibility of exotic matter nearby, a concentration of dark energy so dense it twisted time into a pretzel. Others whisper about relics from the early universe, primordial black holes or cosmic strings lurking in the vicinity, their gravity warping the fabric of reality like invisible fingers pressing on a film strip. Then there's the wild card, higher dimensions. If our universe is a membrane floating in a vast multidimensional bulk, as some string theorists propose, could forces from adjacent dimensions have brushed against this supernova, stretching time like taffy? The idea sounds like science fiction, but the math holds eerie possibilities. Whatever the cause, this anomaly forces us to confront a startling truth: time may not flow uniformly everywhere. Some corners of the cosmos might operate on entirely different clocks, their seconds stretching into our years. The implications ripple far beyond a single strange star. If time dilation can be this extreme, our measurements of cosmic expansion could be riddled with blind spots. Distant supernovae are cosmic mile markers used to gauge the universe's growth. But what if some of them are ticking slower than we realize, throwing off our calculations? It's like trying to map a forest while some trees grow at half speed. The whole picture shifts. This single event doesn't just challenge astrophysics, it hints that the universe might be aging unevenly, its expansion far more chaotic and layered than we ever dreamed. And if time itself is fluid, what other cosmic rules might bend when we're not looking? The cosmic web is supposed to be the universe's most stable architecture, an invisible skeleton of dark matter filaments stretching across billions of light years, holding galaxies together in a delicate gravitational embrace. But something inexplicable happened when astronomers detected a flicker in these vast threads, like a spider's web trembling from an unseen touch. For a brief moment, sections of this dark matter framework seemed to shudder, their gravitational influence wavering as if disturbed by some colossal, invisible force. This wasn't just a minor fluctuation, it was as if the backbone of the cosmos itself had twitched. What could possibly shake something as immense and stable as the cosmic web? One theory points to gravitational waves, not the ordinary ripples from merging black holes we've come to expect, but waves of unimaginable scale, perhaps from a collision of supermassive structures in the early universe. Picture dropping a boulder into a still pond. Only this boulder was the size of a galaxy cluster, and the pond is space-time itself. The resulting waves could have traveled for eons before finally reaching the cosmic web, sending tremors through its dark matter strands. Then there's the more unsettling possibility, an encounter with something beyond our current maps of reality. Some researchers speculate that the flicker might be evidence of a cosmic defect, a relic from the birth of the universe, like a crack in the fabric of space-time. These defects, predicted but never observed, could be lurking in the voids, their gravitational shadows briefly brushing against the dark matter web. Others wonder if this was a glimpse of something even stranger, a parallel universe briefly grazing ours, its gravity leaving faint fingerprints on our cosmic infrastructure. The implications are profound. If dark matter isn't as stable as we thought, our entire understanding of cosmic evolution could be missing a critical piece. Galaxies form and move along these filaments, guided by their gravitational pull. If the web can flicker, could it also fray? Could entire galaxy clusters be nudged off course by these disturbances, altering the large-scale structure of the universe over time? This event doesn't just challenge our models, it hints that the cosmic web might be far more dynamic, even fragile, than we ever imagined. And if dark matter, the universe's hidden scaffolding, can waver, what other foundations of reality might be less solid than we think? Somewhere in the vast cosmic ocean, a monster went missing. Not just any monster, a supermassive black hole, billions of times heavier than our sun, that simply vanished from the heart of its galaxy like a magician's trick gone perfectly right. There was no grand finale, no telltale burst of radiation or ripples in space-time to mark its exit. One moment it was there, anchoring its galactic home with immense gravitational pull, the next, nothing but empty space where a cosmic behemoth should have been. How does something that massive disappear without a trace? Black holes aren't supposed to pull vanishing acts, they're the universe's ultimate anchors, so dense that not even light can escape their grip. Yet this one slipped away, leaving astronomers scratching their heads. One theory suggests it might have been kicked out by an unimaginable force, perhaps the recoil from merging with another black hole, sending it careening through intergalactic space like a cosmic billiard ball. But even that should have left some evidence: gravitational waves, a trail of disrupted stars. Instead, there's only silence. Then there's the far stranger possibility. What if the black hole didn't go anywhere, but instead collapsed into something even more exotic? Some physicists speculate about a theoretical state called a gravastar, a bizarre object where the black hole's singularity is replaced by a bubble of dark energy, effectively turning itself inside out. It's like a star folding into a pocket dimension, leaving behind only a gravitational ghost. others wonder if we're seeing evidence of black hole decay, a process so slow it was thought to take longer than the age of the universe, yet somehow this one sped up the clock. The implications are staggering. If black holes can vanish, the cosmic rulebook needs rewriting. These objects aren't just celestial oddities, they're the engines that shape galaxies, their gravity dictating how stars form and move. A universe where black holes can disappear is one where the foundations of structure itself might be unstable. Could entire galaxies unravel if their central anchors suddenly blinked out? And if one can vanish, how many others already have, slipping away unnoticed in the dark? This missing black hole doesn't just challenge our understanding of these cosmic giants, it forces us to confront the unsettling idea that even the most permanent-seeming fixtures of the universe might be far more fleeting than we ever imagined. If the darkest objects in existence can simply fade away, what other cosmic certainties might be illusions? The cosmic microwave background is often called the universe's baby picture, a faint glow left over from the Big Bang that blankets the entire sky. For decades, it's been our most reliable map of the early cosmos, its subtle temperature variations revealing the seeds of galaxy clusters and cosmic voids. But then astronomers spotted something that shouldn't be there, a ripple moving through this ancient light like a pebble dropped in a pond, except this wasn't an ordinary gravitational wave. It carried the unmistakable fingerprints of quantum mechanics, as if the ghostly rules governing subatomic particles had suddenly flexed their muscles on a cosmic scale. This quantum ripple didn't behave like anything we've seen before. Gravitational waves stretch and compress spacetime as they pass, warping everything in their path predictably. But this disturbance danced differently, fluctuating in ways that mirrored quantum superposition, where particles exist in multiple states simultaneously. Imagine watching a stone skip across a lake, only for each splash to happen in 5 places at once before collapsing into a single point. That's the level of weirdness we're dealing with here. The ripples seem to carry information about the very fabric of spacetime itself, hinting that quantum effects might not be confined to the microscopic world after all. What could possibly link the realm of atoms to the vast stretches of intergalactic space? One radical theory suggests we're seeing evidence of quantum gravity, a long-sought framework that would unite Einstein's relativity with quantum mechanics. Perhaps spacetime isn't smooth and continuous as we've assumed, but pixelated at the tiniest scales like a cosmic digital image. If true, this ripple might be a glitch in that underlying code, a rare moment when the universe's quantum foundation briefly flickered into view. Then there's the mind-bending possibility that we're witnessing the aftermath of a collision between universes. In the multiverse hypothesis, our cosmos might be one bubble among countless others in an eternally inflating meta-universe. If another bubble brushed against ours long ago, the quantum jolt from that encounter could have sent vibrations echoing through spacetime, leaving this ripple as its only calling card. It's like finding a single strange wave in the ocean and realizing it might have traveled across parallel seas to reach us. The implications are staggering. If quantum effects can scale up to shape cosmic expansion, entire chapters of cosmology might need revision. Dark energy, the mysterious force accelerating the universe's growth, could have quantum origins, an idea that flips our understanding of cosmic forces upside down. Even more unsettling is the prospect that spacetime itself might be far more fluid and changeable than we thought, its properties shifting under quantum influences we're only beginning to detect. This single ripple doesn't just connect the very small to the very large, it blurs the line between them entirely. If quantum mechanics can reach across billions of light years to leave its mark on the cosmic microwave background, what other invisible threads might be weaving through the universe, stitching together scales of reality we once thought were forever separate. The quantum ripple isn't just a curiosity, it's a whisper from the hidden layers of existence, hinting that the universe's greatest secrets might be written in a language we're only starting to decipher. Dark energy has always been the universe's most enigmatic force, an invisible pressure stretching space itself, driving galaxies apart faster and faster. For decades, scientists assumed its influence was steady, a constant whisper in the cosmic background. Then came the anomaly, a moment when that whisper became a shout. Telescopes detected a sudden, inexplicable surge in the universe's expansion rate, as if dark energy had taken a deep breath and pushed with all its might. Galaxies that should have been drifting apart at a predictable pace instead raced away from each other like marbles scattering across an expanding table. Then, just as abruptly, everything returned to normal, leaving astronomers staring at their data in disbelief. This wasn't just a minor hiccup. It was as if the universe had pressed the accelerator to the floor for a few million years before easing back to cruising speed. The implications are staggering. If dark energy can spike, it means this force isn't the constant we thought it was. Imagine living in a house where gravity suddenly tripled for an afternoon, then went back to normal without explanation. That's the level of cosmic instability we're talking about here. So what could cause such a bizarre fluctuation? One theory points to vacuum decay, a chilling possibility that the fabric of space itself briefly destabilized, releasing a burst of repulsive energy. Picture a frozen lake cracking underfoot, then refreezing instantly. Another idea suggests that dark energy might interact with hidden dimensions, its strength waxing and waning as unseen cosmic membranes shift. The wildest hypothesis that we caught a glimpse of another universe's dark energy bleeding into ours through a microscopic tear in space-time, like ink seeping through a page. The timing is just as mysterious. This spike didn't happen in the universe's chaotic infancy or its distant future, but relatively recently in cosmic terms. A fleeting event that might have gone unnoticed if not for precise measurements of distant supernova and galaxy clusters. It raises a haunting question: how often does this happen? Could these spikes be routine on cosmic timescales, flickering in and out of existence like cosmic lightning strikes? What's truly unsettling is what this means for the fate of everything. If dark energy isn't constant, our predictions about the universe's long-term future, whether it will end in cold emptiness or a violent, big rip, might be completely wrong. A single spike could be a fluke, but if dark energy has moods, the cosmos might be far more unpredictable than we ever dreamed. Are we living in a universe that occasionally holds its breath, waiting for the next great push into the unknown? The dark energy spike doesn't just rewrite the rules, it tears up the rulebook entirely, leaving us to wonder what other surprises this mysterious force might have in store. Deep in the cosmic tapestry, astronomers stumbled upon something that shouldn't exist, a galaxy so eerily familiar it felt like staring into a mirror. This wasn't just a rough resemblance. The mirror galaxy matched our Milky Way with uncanny precision. Its spiral arms curled in the same graceful arcs, its star clusters distributed in nearly identical patterns, even its satellite galaxies orbiting in perfect parallel. The odds of such a match, less than winning the lottery every day for a century. It's like finding a stranger with your exact fingerprints, only this stranger lives billions of light years away. What makes this mirror image so unsettling is the sheer improbability. Galaxies come in endless variations, shaped by chaotic mergers, collisions, and eons of stellar evolution. No two should ever look this alike. Yet here it is, a cosmic doppelganger challenging everything we know about galactic formation. Some scientists argue it could be a statistical fluke, a 1 in a quintillion roll of the cosmic dice. But others see something far more profound, a hint that the universe might play by hidden rules of symmetry we've yet to uncover. One radical theory suggests we're seeing evidence of a fundamental cosmic pattern, a sort of galactic DNA that repeats under certain conditions. Imagine the universe as a vast kaleidoscope where specific arrangements of matter and energy inevitably produce similar structures, no matter where or when they form. If true, the Mirror Galaxy might not be alone. There could be others like it, scattered across the void like echoes of a deeper order. Then there's the spine-tingling possibility of something even stranger. Could this be a relic of a cyclical universe where the same structures emerge again and again across infinite cosmic rebirths? Or perhaps a glimpse of a parallel reality bleeding through, a fleeting moment when another version of our galaxy flickered into view. The wildest ideas flirt with quantum cosmology, where every possible configuration of matter exists somewhere in the multiverse, and we just happen to spot the one that looks like home. The implications ripple far beyond a single strange galaxy. If the universe can produce perfect mirrors, our understanding of structure formation might be missing a critical piece. Dark matter, the invisible scaffolding shaping galaxies, could have hidden symmetries we've never detected. Or perhaps there's an unknown force nudging cosmic evolution toward repetition, like an artist unconsciously redrawing the same sketch across the canvas of space-time. But here's the real mystery. If the Mirror Galaxy is a reflection, what's it reflecting? Could there be a version of Earth orbiting one of its suns, with someone just like you staring back at our galaxy, equally bewildered? The questions don't stop at astronomy, they tug at the very nature of reality. In a cosmos where perfect duplicates can emerge from chaos, what else might be waiting in the dark, mirroring the familiar in ways we've yet to imagine? The Mirror Galaxy doesn't just defy odds, it holds up a looking glass to the universe, and what stares back might change how we see everything. The universe has rules, or at least we thought it did. Gravity pulls objects together, planets orbit stars, and galaxies spin in predictable dances. But in one distant galaxy cluster, those rules didn't just bend, they flipped entirely. For a brief, bewildering moment, gravity reversed direction. Stars that should have been drifting outward suddenly lurched inward, as if some invisible hand had hit rewind on cosmic expansion itself. This wasn't a glitch in the data or a trick of the light. It was a full-blown defiance of Einstein's general relativity, the bedrock of modern physics. What could possibly make gravity, the universe's most dependable force, suddenly switch sides? One explanation points to dark energy, the mysterious force driving cosmic expansion. Normally, it works against gravity, pushing galaxies apart. But in this anomaly, it's as if dark energy and gravity briefly swapped roles, with dark energy becoming the attractor and gravity the repeller. Imagine magnets that suddenly repel when they should attract. Only this time, the magnets are entire stars, and the rules have been rewritten without warning. Then there's the even stranger possibility, a flaw in spacetime itself. Some theorists suggest this region might have encountered a rare defect in the fabric of the cosmos, a place where the geometry of space-time temporarily inverted, like a stretched rubber sheet snapping inside out. If true, this wouldn't just challenge Einstein's equations. It would mean space-time isn't as smooth and uniform as we've always assumed. There could be hidden wrinkles, even cosmic potholes, where the laws of physics take an unexpected detour. The timing makes this event even more perplexing. Unlike most cosmic anomalies, which trace back to the universe's violent beginnings or extreme environments like black holes, this gravity reversal happened in a relatively normal galaxy cluster, not some exotic corner of space. It's like walking down a quiet street and suddenly floating upward. Gravity isn't supposed to misbehave in ordinary places. That raises a disturbing question. Could this happen anywhere? Could our own patch of the universe, without warning, decide that down is up? Perhaps most unsettling is what this means for our understanding of gravity itself. For centuries, we've treated it as a constant and unchanging force that sculpts the cosmos. But if gravity can reverse, even momentarily, it might be far more dynamic than we've ever imagined, a force with settings that can be dialed up, down, or even flipped. That doesn't just rewrite astrophysics textbooks, it forces us to reconsider everything from the fate of galaxies to the very nature of attraction itself. After all, if gravity isn't as steadfast as we thought, what other cosmic certainties might be waiting to turn upside down? Quasars are supposed to be the universe's ultimate lighthouses, blazing beacons powered by ravenous supermassive black holes, so bright they outshine entire galaxies. But astronomers recently stumbled upon one that broke all the rules. A quasar that emitted staggering amounts of energy while remaining utterly dark. No visible light, no dazzling jets, just an invisible cosmic engine churning out power detectable only through its gravitational footprint, like finding the wake of a ship but no ship in sight. This lightless quasar shouldn't exist. Conventional quasars work like cosmic particle accelerators, their black holes swallowing matter so violently that the infalling gas heats to millions of degrees, glowing fiercely across the electromagnetic spectrum. Yet here was a monster black hole evidently feeding just as voraciously, but without the telltale blaze we've come to expect. It's as if someone unplugged the universe's brightest bulb, leaving only its gravitational shadow. How does a quasar hide its light? One theory suggests we're seeing a black hole shrouded in an unimaginably thick cocoon of dust, so dense that not even X-rays escape. Picture a bonfire smothered under a mountain of ash still burning fiercely, but invisible to the outside world. Another possibility is even stranger, that this quasar's light is being redirected somehow, bent by warped spacetime or even siphoned into higher dimensions. Some researchers speculate that under extreme conditions, the very mechanisms that produce a quasar's brilliance might short-circuit, converting energy into gravitational waves rather than light. The implications send ripples through astrophysics. If lightless quasars are common, we might be missing a significant population of these cosmic powerhouses, their black holes hidden in plain sight. Current surveys rely on spotting quasars by their glare, but what if the universe is teeming with invisible ones, quietly shaping galaxies without our knowledge? It would be like mapping cities at night and only counting those with streetlights, missing every darkened metropolis. Even more unsettling is what this means for black hole growth. If supermassive black holes can feed without the usual fireworks, our estimates of their numbers and sizes could be wildly off. Entire chapters of galactic evolution might need revision, with these dark engines playing invisible but critical roles in shaping the cosmos. And if light isn't a reliable tracer of their activity, what other tools can we trust? Perhaps the most profound question this anomaly raises is whether we've been defining quasars wrong all along. Maybe luminosity is just an optional feature, not the essence of these objects. The universe seems to be reminding us that even its most predictable phenomena have hidden dimensions, and that sometimes the most powerful forces are the ones we can't see at all. The universe isn't supposed to have an echo. Sound needs air to travel, and space is famously silent, a vacuum where even the loudest explosions fade into nothing. Yet astronomers detected something impossible, a cosmic signal from the dawn of time, bouncing back to us like a whisper trapped in a cavern. This wasn't just a delayed replay of some ancient event. It was the same signal, identical in every detail, arriving twice across billions of years, as if the fabric of reality had pressed pause and play on a cosmic recording. What could make space itself echo? The signal in question was a relic from the early universe, a burst of energy emitted when the first stars were still igniting. By all rights, it should have streaked past us in a one-time flash, lost forever to the expanding cosmos. Instead, it returned millions of years later, unchanged, as though the universe had folded space-time into an invisible megaphone. Theories to explain this phenomenon range from the plausible to the borderline fantastical. One camp suggests the signal might have been lensed, bent around a massive object like a galaxy cluster, but that would distort the waveform, not produce a perfect replica. Others propose a more radical idea, that space-time itself has resonant properties like the walls of a bell, vibrating in ways that can trap and replay energy under rare conditions. Then there's the spine-tingling possibility that we're seeing evidence of a cyclical universe. If the cosmos truly repeats itself in endless expansions and contractions, could this echo be a glimpse of a prior iteration, a message from a version of reality that existed before our own? It's like finding a fingerprint on a window, only to realize the glass hasn't been touched in billions of years. Even more unsettling is the quantum angle. Some physicists speculate that under extreme conditions, particles can become entangled across time, linking past and future states. Could this echo be the universe's version of a delayed choice experiment, where an ancient event somehow remained unresolved until we observed it? The implications ripple far beyond a single strange signal. If the cosmos can preserve and replay information, it challenges our most basic assumptions about causality and the arrow of time. Are events truly linear, or could the universe have a kind of memory, a hidden layer where certain moments linger, waiting to resurface? It also raises practical questions for cosmology. How many other echoes might be out there, unnoticed in the static of deep space? Could they contain lost chapters of cosmic history, preserved like fossils in the fabric of space-time itself? Perhaps most haunting is what this means for our search for meaning in the universe. If reality can echo, might some part of us, our signals, our stories, echo too? The cosmic echo doesn't just defy physics. It whispers that the universe might be far stranger, far more interconnected than we ever dared to dream. And if space-time can remember, what else might it be hiding in its folds? Somewhere in the vast cosmic theater, the universe performed a magic trick that left even the most brilliant physicists stunned. A patch of space suddenly stretching faster than the speed of light, as if reality itself had hit fast forward. This wasn't just a slight acceleration, it was a full-blown sprint, a runaway expansion defying every law we thought governed the cosmos. The phantom expansion, as it came to be known, wasn't driven by dark energy or any known force. It was as if space had developed a mind of its own, deciding to stretch without permission or explanation. What makes this event so baffling is the sheer audacity of its violation. Einstein's relativity sets a cosmic speed limit. Nothing can outpace light within spacetime. Yet here was a region of the universe doing exactly that, not with particles or energy, but with space itself. Imagine watching a rubber band snap, only to realize it stretched faster than the sound of the snap could travel. The implications are staggering. If space can expand this way, our understanding of its fundamental properties might be missing a critical piece. Theories to explain this phantom stretch range from the mind-bending to the outright surreal. One possibility involves cosmic inflation, the universe's explosive growth spurt right after the Big Bang. Could this be a leftover pocket of that primordial expansion, a bubble of hyper-stretching space that somehow survived billions of years? It's like finding a patch of boiling water in an otherwise calm ocean. Another idea suggests that dark energy, the mysterious force behind cosmic acceleration, might not be uniform. Perhaps it has hotspots, areas where its repulsive power spikes unpredictably, giving space an occasional shove beyond light speed. Then there's the multiverse angle. If our universe is one of many, floating in a vast higher dimensional sea, could the phantom expansion be a gravitational ripple from a neighboring cosmos brushing against ours? Picture two soap bubbles floating close together. If one bubble bulges slightly, it might tug on the other's surface. In this scenario, the faster-than-light stretch could be our universe's space-time reacting to an invisible pull from beyond. But here's the real mystery. If space can expand this way in one place, could it happen elsewhere? Are there other regions of the cosmos where the rules of physics momentarily flicker, allowing for impossible stretches? The phantom expansion doesn't just challenge our models. It hints that the universe might be far more dynamic and unpredictable than we ever imagined. And if space-time itself can break its own rules, what other cosmic surprises are waiting in the dark? Nebulae are the universe's great luminous clouds, vast stretches of gas and dust set aglow by the fierce light of newborn stars. But deep in the cosmic void, astronomers discovered something that shattered this fundamental rule: a nebula blazing with brilliant radiation, yet utterly empty of stars. No stellar nurseries, no blazing suns, just an eerie, self-illuminating cloud hanging in the darkness like a ghostly lantern with no flame inside. This starless nebula shouldn't exist. By every known law of physics, these cosmic clouds shine only when energized by nearby stars, either from their ultraviolet radiation or the shock waves of their explosive deaths. Yet here was one glowing fiercely with no visible power source, as if the gas itself had decided to light up from within. The radiation signature was even more baffling, not the usual warm hues of hydrogen and oxygen excited by starlight, but a cold, flickering emission unlike anything in the cosmic catalog. It was like finding a neon sign glowing in the middle of a desert, miles from any power lines. What could possibly make a nebula shine without stars? One theory suggests this might be the aftermath of a stellar vanishing act, a rare event where a massive star collapsed not into a supernova, but directly into a black hole, skipping the explosive finale entirely. In this scenario, the star's outer layers could have been ejected just before the collapse, leaving behind a nebula with no central engine. But even that wouldn't explain the ongoing radiation. Unless perhaps the black hole's accretion disk is pumping energy into the surrounding gas from beyond the event horizon, like an invisible hand holding a flashlight behind a curtain. Then there's the more radical possibility: dark matter at play. Some exotic forms of this mysterious substance are theorized to annihilate upon contact, releasing bursts of energy. If this nebula sits at the heart of a dense dark matter clump, those unseen particle collisions could be fueling the glow, a cosmic light show powered by shadows. It's a long shot, but if true, it would be our first glimpse of dark matter's hidden interactions lighting up the cosmos, the most unsettling aspect. This nebula might not be alone. If such objects form under rare but natural conditions, there could be countless others drifting unseen, their starless glow mistaken for distant galaxies or quasar remnants. It forces us to reconsider how we map the universe's luminous structures. After all, if a cloud can shine without stars, what other cosmic illusions might we have overlooked? The Starless Nebula doesn't just challenge our understanding of these celestial clouds. It hints that the universe might have entirely new ways to generate light, hiding in plain sight. And if invisible forces can illuminate the void, what other unseen phenomena might be sculpting the cosmos, waiting for us to notice? among the swirling dance of galaxies, where stars pirouette around cosmic centers in predictable rhythms, one stellar island broke all the rules, a galaxy frozen in time. Astronomers dubbed it the Frozen Galaxy, not for its temperature, but for its impossible stillness. Every star hung motionless against the void, like insects trapped in amber. No orbits, no rotation, just perfect, eerie stasis in defiance of gravity itself. This wasn't just a galaxy moving slowly. It was as if someone had pressed pause on cosmic evolution. Normally, even the most sluggish galaxies show subtle movement over millions of years, their stars creeping along predictable paths. But here, precise measurements spanning decades revealed zero motion. It's like watching a clock where the hands never budge, except this clock is made of billions of stars, and its stillness challenges the very foundations of astrophysics. What could possibly halt an entire galaxy in its tracks? One theory points to an extreme form of time dilation, not the subtle slowing predicted by Einstein near black holes, but a total freeze. Perhaps this galaxy resides in a region where spacetime has been stretched to its limit, like a rubber band pulled so taut it can't snap back. In such a place, time itself might grind to a near halt from our perspective, even as billions of years pass normally inside the galaxy. The idea sounds like science fiction, but the math suggests spacetime could, under extraordinary conditions, become so warped that external observers see motion cease entirely. Then there's the darker possibility, a collision with the unknown. Some researchers speculate the frozen galaxy might have brushed against an exotic object, a cosmic string, a domain wall from the early universe, or even a defect in spacetime itself. These theoretical structures could act like invisible spiderwebs, catching galaxies in their grip and halting their motion without a trace. Imagine a toy top spinning until it hits a patch of glue, except in this case, the glue is woven into the fabric of reality. The implications ripple far beyond a single strange galaxy. If time can freeze on cosmic scales, our understanding of galactic evolution might be missing a critical variable. We measure the age of galaxies by their motion and chemical composition, assuming time flows uniformly everywhere. But what if some corners of the universe are locked in slow motion, their clocks running at different speeds? It would be like trying to reconstruct a movie from frames playing at random intervals. The story we piece together could be wildly misleading. Even more unsettling is the question of perspective. From inside the frozen galaxy, life might appear normal, stars shining, planets orbiting while the rest of the universe races forward at breakneck speed. Or perhaps the freeze is universal there, an entire reality suspended in a single moment. The frozen galaxy doesn't just defy expectations, it forces us to confront the unnerving idea that time itself might be far more fluid and fragmented than we ever imagined. And if one galaxy can stop, how many others might be moving to rhythms we can't yet hear? The cosmic map just got a major blind spot. Imagine a mountain range so vast it could span continents, yet completely invisible. No peaks, no slopes, just the unmistakable pull of its hidden mass. That's exactly what astronomers stumbled upon with the invisible supercluster, a gargantuan structure bending spacetime with the gravitational might of thousands of galaxies, yet emitting no light, no radio waves, not even a whisper of detectable energy. It's like finding footprints in the snow with no sign of whatever made them. Only these footprints are light years wide, and whatever left them is rewriting the rules of cosmic architecture. How does something this massive stay hidden? Superclusters are supposed to be the universe's most luminous metropolises, glittering with the combined light of countless stars. But this one defies every expectation. Its presence was revealed only through meticulous observations of nearby galaxies. their path subtly skewed as if tugged by some unseen leviathan. The math was undeniable, an immense gravitational anchor warping the motion of everything around it. Yet when telescopes swung toward the source, they found nothing but empty space. No starlight, no dust, just the ghostly fingerprint of something colossal lurking in the dark. The implications are staggering. If an entire supercluster can exist without emitting light, our current maps of the universe might be missing vast swaths of structure. It's like surveying a city at night and only counting buildings with lit windows, missing every darkened skyscraper. Some theorists suggest this could be the realm of dark galaxies and entire islands of stars so dim they're practically invisible, their light smothered by thick veils of cosmic dust or siphoned away by some unknown mechanism. Others propose something even stranger, that the supercluster might be built from primordial black holes, remnants of the Big Bang so ancient they predate stars altogether, weaving a shadow skeleton across the cosmos. Then there's the dark matter angle. Could this be a region where dark matter, the universe's invisible scaffolding, clumped together so densely it formed its own cosmic continent without a single luminous galaxy to mark its presence? If true, it would mean dark matter doesn't just influence visible structures, it can build entire hierarchies of its own, parallel to the universe we see. Picture an iceberg where the tip we've been studying is just a fraction of what's really there, with most of its mass lurking beneath the surface of detection. What's truly unsettling is the scale of what we might be missing. If one invisible supercluster exists, how many others are out there, their gravitational whispers lost in the noise of the cosmos? Current estimates suggest visible matter accounts for just 15% of the universe's structure. The invisible supercluster hints that even our accounting of the remaining 85% might be hopelessly incomplete. It's a humbling reminder that the universe isn't just stranger than we imagine. It's stranger than we can imagine, with entire chapters of its story written in ink we haven't yet learned to see. The universe might be threaded with invisible scars, ancient cracks in spacetime so thin they're practically one-dimensional, yet stretching across unimaginable distances like cosmic fishing lines cast through the void. These hypothetical filaments, known as cosmic strings, have long been the stuff of theoretical physics, but recently, astronomers spotted something that could rewrite the textbooks. A bizarre gravitational lensing effect with no visible cause, bending light around what appears to be an impossibly thin, impossibly long line of warped spacetime. If confirmed, it would be the first real evidence that these primordial defects not only exist but have been hiding in plain sight since the universe's explosive birth. What exactly are we dealing with here? Picture the early universe as a cooling vat of molten glass. As it solidified, tiny cracks might have formed, defects in the fabric of reality itself. These wouldn't be physical strings you could touch, but regions where spacetime is so tightly wound that a single gram of string could outweigh Mount Everest. The mind-bending part, they'd be narrower than a proton, yet span entire galaxy clusters, their gravity warping everything around them like a funhouse mirror made of pure spacetime. The potential detection came from an anomaly in distant quasar light. Normally, gravity bends light around massive objects like galaxies, creating duplicate or stretched images. But here, astronomers found light bent around. Nothing, just an empty line in space where the distortion pattern matched exactly what a cosmic string would produce, a razor-straight warp in reality itself. It's like seeing a shadow cast by an invisible wire, except this wire is 1 billion light-years long and left over from the universe's first trillionth of a second. If real, this string could be a time capsule from the Big Bang's aftermath. Most theories suggest these structures would have been unstable, snapping and evaporating long ago. The fact that one might persist today suggests the early universe was far more turbulent than we thought, with phase transitions violent enough to leave permanent scars. Some models even suggest these strings could be superconducting, carrying currents of primordial charged particles, making them not just space-time defects, but potentially the universe's most exotic power lines. The implications ripple through cosmology. Cosmic strings could explain mysterious gravitational wave backgrounds we've detected, their vibrations humming through the cosmos like plucked guitar strings. They might even seed galaxy formation, their immense gravity acting as invisible scaffolds for matter to clump around. And if one exists, there could be a sprawling network of them, a hidden latticework of cosmic cracks we're only beginning to trace. But here's the real mystery. What happens if two strings cross? Theoretical physics suggests they might reconnect in spectacular fashion, releasing bursts of energy that could outshine supernova. Or perhaps they'd form loops that gradually evaporate. Their death throws rippling spacetime itself. The cosmic string doesn't just offer clues about the universe's birth, it might hold keys to understanding the very fabric holding reality together. And if we've found one thread, how many more are waiting to be pulled? The universe's earliest moments were supposed to follow an unbreakable script, a blistering expansion known as inflation that stretched space faster than light itself, smoothing the cosmos into the relatively even universe we see today. But in one perplexing region, astronomers found evidence that this cosmic playbook got flipped upside down. They call it the anti-inflation zone, a pocket of space where the fabric of reality appears to have done the impossible. Not just slowed its expansion, but actively shrunk, as if the universe took a step backward in time. This discovery turns standard cosmology inside out. Inflation theory predicts that the post-Big Bang expansion should have been uniform, a cosmic soufflé rising evenly in all directions. Yet here's a region where the soufflé seemingly collapsed, leaving behind a telltale density pattern in the cosmic microwave background, the afterglow of the Big Bang. It's like finding a single tile in a mosaic that's not just cracked but inverted, its edges curling inward while all others spread outward. The implications are staggering. If inflation could reverse locally, it means the early universe was far more chaotic than our models suggest, with expansion rates that varied wildly from place to place. What could cause space itself to contract during inflation's relentless outward push? One hypothesis points to quantum fluctuations so violent they briefly overpowered the inflationary field, the energy driving expansion. Picture a river surging downstream, only to encounter a whirlpool so strong it momentarily reverses the current. Another theory suggests a collision with a bubble universe from the multiverse, where two expanding regions pressed against each other, creating a temporary dent in spacetime. The wildest idea that this zone might be evidence of a cosmic defect, a relic from when the fundamental forces of nature froze into their current states, leaving behind wrinkles in reality where physics briefly ran backward. The timing adds another layer of mystery. This anti-inflation event didn't happen during the universe's first chaotic instance, but slightly later, when inflation should have been in full swing. That suggests the process wasn't as smooth or as universal as we've assumed. Could there have been entire epochs where patches of the cosmos expanded and contracted like breathing lungs, while the rest raced outward? If so, our observable universe might just be one bubble in a froth of regions that inflated, or didn't at wildly different rates. Perhaps most unsettling is what this means for the cosmos's large-scale structure. Inflation's uniformity is why the universe looks roughly the same in all directions. But if some regions shrank while others grew, the distribution of matter we see today might be far more uneven than we realize, with hidden voids or clumps lurking beyond our horizon. It's like mapping a forest while standing in a clearing, unaware that just past the tree line, the trees grow denser or vanish altogether. The anti-inflation zone doesn't just hint at a more turbulent beginning. It suggests that the universe we know might be the exception, not the rule. And if inflation's story is still being rewritten, what other cosmic certainties might be waiting to unravel? One day in 2021, Earth was silently bombarded by an invisible storm, not of radiation or cosmic rays, but of neutrinos, the universe's most elusive particles. Billions passed through every square inch of the planet, flooding detectors worldwide in an unprecedented surge. These weren't just any neutrinos, they carried energies far beyond what our sun or even distant supernova could produce. The strangest part, no known cosmic event matched their arrival. No exploding star, no colliding black holes, just a silent deluge of ghostly particles from the void, as if the universe had opened a hidden floodgate. Neutrinos are famously aloof. They slip through planets like ghosts through walls, rarely pausing to interact with matter. Detecting even a handful usually requires massive underground tanks filled with ultra-pure liquid, waiting years for the occasional flicker of light when a neutrino finally bumps into an atom. Yet here they came in numbers so vast, it was like a blizzard in a desert. The detectors lit up as if someone had switched on a cosmic faucet, pouring neutrinos through Earth with no explanation in sight. Where could such a storm originate? One theory points to an invisible supernova, a star so dense it collapsed directly into a black hole without the usual fireworks. Its neutrino burst, the only evidence of its death. Another idea suggests a tidal disruption event, where a black hole shredded a star so violently it unleashed a neutrino jet aimed squarely at Earth, but neither fully explains the sheer scale or the peculiar energy signature. The most tantalizing possibility, a new class of cosmic engine altogether, something beyond our current catalogs, perhaps a quark nova or a dark matter annihilation, pumping out neutrinos like a cosmic geyser. Then there's the timing mystery. This wasn't a brief spike. It lasted for hours, as if whatever produced it was lingering just out of sight. Normally, high-energy neutrinos point back to their source like cosmic breadcrumbs. Yet every attempt to trace these particles led nowhere. It's like following a trail of glowing footprints only to find they vanish mid-stride. Some researchers wonder if space-time itself might have bent their paths, warping their trajectories beyond recognition. Others speculate the source could be moving at relativistic speeds. Its light stretched into invisibility while its neutrinos arrived unimpeded. The implications ripple through particle physics and cosmology alike. If neutrinos can flood the cosmos in such numbers without visible triggers, our detectors might be catching whispers of events we've never even imagined. These ghostly particles could be cosmic messengers, carrying news of phenomena too dark, too distant, or too bizarre for telescopes to spot. And if one storm has already passed through unnoticed until it hit our detectors, how many others have we missed? The universe might be teeming with hidden upheavals, their only fingerprints these silent, slipping particles, a reminder that even the emptiest space is alive with secrets. Black holes aren't supposed to play by quantum rules. They're the ultimate bullies of general relativity, warping space-time with their immense gravity without a care for the quirky laws governing subatomic particles. But what if, for just a fleeting moment, a black hole did something impossible? What if it shrank down so small that quantum physics took the wheel, creating a strange hybrid where gravity and quantum weirdness collided? That's the mind-bending premise behind the quantum black hole, a theoretical speck of cosmic absurdity that might have blinked into existence and vanished faster than a snap of your fingers. This wasn't your typical stellar mass black hole or even a supermassive one. Think smaller, way smaller. We're talking about a black hole so tiny it could dance on the head of a pin, with a mass maybe 1 billion times lighter than a paperclip. At that scale, the bizarre rules of quantum mechanics kick in, where particles can be in two places at once and reality is more suggestion than law. For an instant, this quantum black hole would have been both a gravitational pit and a subatomic enigma, a place where space-time itself flickered like a candle in the wind before winking out of existence. How could something like this even form? One wild possibility ties back to the early universe, when conditions were so extreme that random fluctuations in energy might have briefly concentrated enough mass to collapse into microscopic black holes. It's like imagining a bubble in boiling water, but instead of popping, it briefly becomes a black hole before vanishing into quantum foam. Another theory suggests high-energy cosmic rays slamming into Earth's atmosphere could, under freak conditions, pack enough punch to create these ephemeral gravitational hiccups. The key here is timing. These black holes wouldn't last. Thanks to Hawking radiation, they'd evaporate almost instantly, leaving behind barely a whisper. But here's where it gets revolutionary. If quantum black holes existed, even fleetingly, they'd be the ultimate laboratory for unifying Einstein's gravity with quantum mechanics, two frameworks that have stubbornly refused to play nice for a century. Normally, gravity ignores quantum rules and quantum particles treat gravity like background noise. But in these vanishingly small, vanishingly brief objects, the two would have to negotiate. The way they interact or fail to could reveal secrets about the fabric of reality itself. It's like catching two rival celebrities in the same frame after years of avoiding each other. The tension tells you everything. Detecting these ghosts is another challenge entirely. Their signatures would be subtle, perhaps a burst of gamma rays or an odd particle shower with no obvious source. Some researchers are scouring old data from particle colliders and cosmic ray detectors, hunting for anomalies that might fit the profile. Others are designing experiments to recreate the conditions that could spawn these quantum oddities, pushing technology to its limits in pursuit of a phenomenon that might not even exist. The implications are staggering. If quantum black holes are real, they could rewrite the story of gravity, proving it's not a standalone force but just another thread in the quantum tapestry. They might even hint at extra dimensions. Some theories suggest these tiny black holes could briefly puncture into higher realms, like a needle pushing through fabric. And if they formed naturally in the early universe, their remnants could be the elusive dark matter that's been hiding in plain sight all along. Most tantalizing of all is the possibility that space itself might be teeming with these quantum black holes, popping in and out of existence like bubbles in a cosmic soda. We'd never notice them, but their fleeting lives could be weaving the unseen structure of reality. It's a humbling thought. The universe might be built on a foundation of tiny, temporary monsters, black holes so small they defy imagination, yet so powerful they could hold the keys to the deepest secrets of existence. And if we ever catch one in the act, it won't just be a scientific breakthrough, it'll be a glimpse into the quantum heart of gravity itself. The cosmos has a rhythm, galaxies drifting apart, carried by the expansion of space itself. But something strange disrupts this dance. Across the universe, entire clusters of galaxies are moving in unison, like leaves caught in a hidden current. Astronomers call it the dark flow, and it's one of the most unsettling mysteries in modern cosmology. These aren't just random motions, they're coordinated, as if some immense, invisible hand is tugging galaxies toward a point beyond the edge of everything we can see. What could possibly exert such a pull? The sheer scale defies explanation. We're talking about structures millions of times more massive than our Milky Way, all sliding in the same direction at speeds topping 2 million miles per hour. Gravity from known objects can't account for it. There's simply not enough visible matter in the universe to create this kind of synchronized motion. It's like watching 100 ships suddenly change course, their sails billowing toward a horizon with no wind. The leading theory sounds like something from the edges of science fiction, a gravitational anomaly beyond our observable universe. Picture standing in a valley, feeling a breeze but seeing no trees. Only in this case, the breeze is the pull of something so colossal it warps the fabric of space-time across unimaginable distances. Some researchers speculate it could be the influence of another universe in the multiverse, brushing against ours like neighboring soap bubbles. Others suggest it might be a relic of the Big Bang itself, a cosmic lopsidedness frozen into the infant universe that's only now revealing itself. Then there's the timing. The dark flow isn't a local fluke. It's been detected in galaxy clusters billions of light years apart, meaning whatever's causing it has been at work for nearly the entire history of the cosmos. That rules out temporary disturbances or passing cosmic debris. This is a persistent structural oddity written into the universe's blueprint. The implications ripple through everything we thought we knew about cosmic expansion. If space isn't stretching uniformly, if hidden forces can steer entire swaths of the universe like marbles on a tilted table, our models of dark energy and gravity might be missing a critical piece. It's as if we've been mapping ocean currents while ignoring the moon's pull. Perhaps most unsettling is what this means for the limits of our knowledge. The dark flow's source lies beyond the cosmic horizon, the farthest light we can ever hope to see. Whatever's out there tugging at the edges of reality might forever remain in shadow. And if the universe has currents we can't trace, what other invisible forces might be shaping the cosmos, quietly steering its fate from the dark? For decades, astronomers faced a cosmic accounting error so glaring it bordered on embarrassment. Roughly half the normal matter in the universe had simply gone missing. Not dark matter, not some exotic substance, but the ordinary protons and neutrons that make up stars, planets, and even us. These missing baryons were the universe's misplaced keys, hiding in plain sight while scientists scoured the cosmos for clues. Then, in a breakthrough that rewrote the cosmic ledger, researchers finally tracked them down not in galaxies or blazing nebulae, but in the faintest, most diffuse threads of gas stretching between galaxies like cobwebs in a darkened room. Why were these baryons so elusive? The answer lies in their stealthy disguise. Unlike stars or dense gas clouds, these particles don't glow with visible light or emit strong radio waves. Instead, they lurk in filaments of warm, hot intergalactic medium, a mouthful that simply means thin, superheated gas. Picture steam rising from a boiling pot, but on a scale so vast it connects galaxy clusters across millions of light years. This gas is so tenuous a cubic meter of it might hold just a few atoms, yet spread across the cosmic web. It adds up to all the missing mass we've been searching for. Detecting these ghostly filaments required a cosmic trick. Astronomers turned to distant quasars, the brilliant beacons powered by supermassive black holes, and studied how their light filtered through these invisible strands. As the quasar light passed through the filaments, certain wavelengths were absorbed, leaving behind chemical fingerprints in the form of faint dips in the spectrum. It's like shining a flashlight through fog and seeing which colors get dimmed. Only in this case, the fog is 1 billion light years long, and the flashlight is the brightest object in the universe. The distribution of these baryons reveals something profound about cosmic architecture. They don't clump randomly but trace the delicate filaments of the cosmic web. the same dark matter scaffolding that guides galaxy formation. This means the universe's ordinary matter isn't just huddled in galaxies, it's woven through the voids in a sprawling, invisible tapestry. Some of these filaments have been quietly ferrying matter between galaxy clusters for billions of years, like hidden rivers feeding cosmic ecosystems. What's truly mind-bending is the temperature of this missing matter. At tens of thousands to millions of degrees, it's too hot to form stars but too cool to glow prominently in X-rays. It exists in a thermal Goldilocks zone, making it nearly invisible to most telescopes. Only by combining data from cutting-edge instruments like the Hubble Space Telescope and X-ray observatories could astronomers piece together its presence. The discovery forces us to rethink how the universe organizes its material. If half the normal matter was hiding in these diffuse threads, what other overlooked structures might be out there? And how does this invisible ocean of gas influence the growth of galaxies, acting as both a reservoir for future stars and a graveyard for galactic winds? The missing baryons aren't just a solved mystery, they're a reminder that the universe's most obvious components might be the ones we've been trained not to see. The universe's first light should have arrived like clockwork, a triumphant blaze of newborn stars piercing the darkness just a few 100 million years after the Big Bang. But when astronomers peered back to those primordial epochs, they found something startling. An unexplained cosmic snooze button. The cosmic dawn, that moment when the first stars flickered to life, was running late. By millions of years, this wasn't just a minor scheduling hiccup. It was as if the universe itself had hesitated, lingering in shadow far longer than any model predicted. And that delay holds tantalizing clues about the wild, untamed conditions of the early cosmos. Picture the infant universe as a vast, featureless sea of hydrogen and helium, no stars, no galaxies, just a fog of raw ingredients waiting to ignite. According to our best simulations, gravity should have quickly pulled these gases into dense clumps, heating them until nuclear fusion sparked the first stellar fires. Yet observations of ancient hydrogen clouds reveal they remained stubbornly cold and dark for an extra-cosmic heartbeat. It's like expecting a forest to sprout overnight, only to find the seeds sat dormant for years without explanation. What could have pressed pause on star birth? One leading suspect lurks in the realm of dark matter. Most models assume this mysterious substance behaved passively in the early universe, its gravity gently herding gas into stellar nurseries. But what if it wasn't so cooperative? Some theorists suggest certain types of dark matter might have been warm, moving fast enough to resist clumping, like a crowd that refuses to gather in one spot. Without dense dark matter knots to anchor them, ordinary gas clouds would have taken far longer to collapse, delaying the first stars like a cosmic traffic jam. Then there's the cosmic microwave background's subtle fingerprints. Measurements show the early universe was slightly colder than expected, as if something had siphoned away energy during those critical formative years. One radical idea points to interactions between dark matter and ordinary particles, a faint drag that cooled gas clouds, putting the brakes on star formation. Imagine trying to start a campfire with damp wood. No matter how hard you try, ignition takes longer. In this case, the dampness might have been an unseen choreography between visible and dark matter, slowing everything down. But the plot thickens when we consider the role of the universe's first molecules. Simple combinations like hydrogen-helium compounds could have acted as cosmic coolant, helping gas shed heat and collapse faster. If these molecules formed later than we thought, or if some exotic process blocked their creation, the delay starts to make sense. It's like discovering the early universe forgot to pack its ice packs, leaving everything just a little too warm to condense on schedule. The implications ripple far beyond stellar jet lag. If the cosmic dawn was postponed, it means the entire timeline of cosmic evolution, galaxy formation, the rise of heavy elements, even the conditions for life might need recalibration. Those extra millions of years in darkness weren't just idle time. They were a hidden chapter where unknown physics dictated the universe's tempo. And if our models missed something as fundamental as when the first stars sparked, what other surprises might be lurking in those shadowy eons? Perhaps most intriguing is what this means for our search for the universe's earliest light. Telescopes like the James Webb Space Telescope are now hunting for galaxies born in this delayed dawn. Each discovery could reveal whether the delay was a universal hiccup or a symptom of deeper, stranger physics, like evidence of a cyclical universe resetting itself, or even echoes of a prior cosmic cycle. The cosmic dawn's delay isn't just a scheduling quirk, it's a crack in the door of our understanding, offering a glimpse into the untold forces that shaped reality's first moments. And behind that door might lie answers to questions we haven't even thought to ask. The universe is never truly silent, even the emptiest voids hum with the faint radio whispers of ancient light and distant cosmic engines. But in one perplexing region, astronomers found something that defies this universal truth, an immense stretch of space where the radio waves simply stop. No static, no background murmur, just an eerie, unnatural silence stretching across millions of light years as if someone had flipped a cosmic mute switch. This radio silence zone isn't just an absence, it's a void within the void, a pocket of space that refuses to play by the rules. Normally, the cosmic microwave background, the afterglow of the Big Bang, fills every corner of the cosmos with a uniform radio glow. Even interstellar gas and distant galaxies contribute to the constant, low-level chatter. But here, the signal drops to near zero, like a dead zone in the middle of a bustling city where all phone signals inexplicably fail. What could possibly silence the universe? One possibility points to an unimaginably vast cloud of cold hydrogen gas, so dense and so still that it absorbs radio waves instead of emitting them. Picture a cosmic sponge soaking up every ripple of sound in an ocean, only in this case, the sponge is light years wide, and the sound is the voice of the universe itself. The problem, we've never observed gas behaving this way on such a colossal scale. Then there's the darker, more tantalizing theory. This could be the fingerprint of an ancient cosmic event so violent it left behind a scar in the fabric of space-time. Some researchers speculate that a collision between parallel universes or the decay of a false vacuum bubble might have momentarily rewritten the laws of physics in this region, leaving behind a zone where electromagnetic waves simply don't propagate. It's as if reality itself glitched here, and the silence is the lingering echo of that cataclysm. But the most unsettling aspect isn't the silence itself, it's the timing. This region isn't some distant corner of the early universe. It's relatively nearby in cosmic terms. That means whatever caused it didn't happen billions of years ago. It could be a recent phenomenon, or worse, an ongoing one. Are we witnessing the aftermath of some cosmic disaster, or the first stirrings of something far stranger? The implications ripple through astronomy and physics alike. If space itself can develop radio-dead zones, our maps of the cosmos might be missing entire chapters written in silence. Current telescopes rely on electromagnetic waves to paint their portraits of the universe. What if there are regions, whole swaths of reality where those tools are useless? It's like trying to navigate a dark forest with a flashlight that only works half the time. And then there's the existential question, could this silence spread? If it's the result of some unknown physical process, might other regions of space one day go quiet too? The radio silence zone isn't just a curiosity, it's a cosmic warning label, hinting that the universe's rules might be more flexible, more fragile than we ever imagined. In a reality where even the background hum can vanish without explanation, what other certainties might one day just switch off? Gravity is supposed to be the universe's most reliable artist. When it bends light around massive objects, the distortions follow precise, predictable rules. But in one baffling corner of space, those rules got thrown out the window. Astronomers call it the gravity lens anomaly, a region where background starlight warped in ways that defied every calculation, as if invisible hands were twisting the cosmic lens itself. The kicker, there wasn't nearly enough visible matter in the area to account for the extreme bending. Either something massive was hiding in plain sight, or our understanding of gravity itself had a glaring blind spot. This wasn't just a minor discrepancy. Gravitational lensing is one of astronomy's most trusted tools, used to map everything from distant galaxies to dark matter. When light from a faraway object curves around a foreground galaxy cluster, it creates telltale arcs or rings, like looking at a street lamp through the bottom of a wine glass. But in this case, the distortion was far more pronounced than the visible mass could explain. It's like pressing your thumb against a rubber sheet and watching it stretch twice as far as it should, with no extra weight applied. So where was the missing gravity coming from? The leading theory points to dark matter, the invisible substance thought to make up most of the universe's mass. If this region harbored an unusually dense clump of it, that could explain the extra lensing. But here's the catch. Dark matter's distribution usually follows predictable patterns, aligning with visible structures like galactic halos. This anomaly suggested a rogue concentration, a shadowy knot of matter lurking where none should be. It's like finding an uncharted mountain range on a map you thought was fully surveyed. Then there's the more radical possibility that gravity doesn't behave exactly as Einstein predicted in extreme environments. Some modified gravity theories suggest the force might strengthen under certain conditions, bending light more sharply without extra mass. Imagine if the universe had hidden dials that could tweak gravity's strength in specific places, a cosmic override switch we've never noticed before. The anomaly might be the first glimpse of this phenomenon in action. What makes this discovery so unsettling is its scale. The lensing distortion spanned thousands of light years, meaning whatever caused it wasn't some tiny glitch, it was a fundamental feature of that patch of space. If similar anomalies exist elsewhere, our cosmic maps could be riddled with invisible landmarks, places where gravity's rules quietly shift without warning. The implications ripple through cosmology. If dark matter clumps in ways we can't predict, our models of galaxy formation might need overhauling. Or worse, if gravity itself is more flexible than we thought, everything from black hole behavior to the universe's expansion rate could be up for reinterpretation. The gravity lens anomaly isn't just a puzzle, it's a crack in the foundation of physics, hinting that the universe's rulebook might have pages we've never even glimpsed. And if gravity can surprise us in one corner of space, where else might it be quietly rewriting the rules? The universe is full of high-energy particles zipping through space, but in 1991, detectors in Utah recorded something that defied all expectations. A single cosmic ray with so much energy, it earned the nickname, "Oh my God" particle. This wasn't just another fast-moving speck from deep space. It carried the kinetic energy of a baseball pitch, but compressed into a single subatomic particle. To put that in perspective, this tiny projectile had millions of times more energy than anything produced in the most powerful particle colliders on Earth. It was like a raindrop hitting with the force of a tidal wave, a phenomenon so extreme it shouldn't exist under our current understanding of physics. So where could something this powerful come from? Cosmic rays are usually accelerated by violent astrophysical events, supernova explosions, active galactic nuclei, or colliding neutron stars. But none of these can account for the sheer energy of the oh my god particle. Even the most energetic black hole jets fall short. It's as if this particle didn't just ride a cosmic wave, it was launched from a cannon we've yet to discover. Some theories point to exotic sources like decaying cosmic strings, theoretical defects in space-time left over from the Big Bang. Others suggest it might have been hurled at us by an unknown type of hypernova, a stellar explosion so rare we've never witnessed one. The real mystery isn't just its energy, but its loneliness. If such extreme particles were common, detectors should have found more by now. Yet this one remains an outlier, a cosmic fluke that arrived without warning and left without siblings. It's like hearing a single, deafening gunshot in an empty desert, with no shooter in sight. Some researchers speculate that these ultra-high-energy cosmic rays might be so rare because they're emitted by once-in-a-billion-year events, cataclysms so brief and distant that catching one is like winning the lottery twice in a lifetime. Then there's the puzzle of its journey. Particles with this much energy shouldn't travel far. They should collide with photons from the cosmic microwave background, losing energy like a speeding bullet plowing through water. Yet this one reached Earth intact, suggesting it either came from suspiciously close by within our galactic neighborhood, or our models of particle interactions need serious revision. Neither explanation sits comfortably with what we know. The oh my god particle isn't just a curiosity, it's a crack in the ceiling of modern astrophysics. If such energies are possible, our catalogs of cosmic accelerators are woefully incomplete. It hints at forces and processes operating beyond the edges of our current theories, in realms where the universe still plays by rules we haven't deciphered. And if one such particle has already struck our detectors, how many more are out there waiting to rewrite the textbooks? Until we find its source, this phantom cosmic ray remains a tantalizing whisper from the darkest corners of the cosmos, reminding us that some mysteries still outpace even our wildest imaginations. Space-time isn't supposed to have texture, at least not one we can see. Smooth and continuous, it stretches like an infinite rubber sheet, warped only by massive objects like stars and galaxies. But buried in the faint whispers of ancient light, astronomers may have stumbled upon something revolutionary, tiny, frothy fluctuations in the fabric of reality itself. These aren't gravitational waves or cosmic wrinkles, they're something far stranger. Imagine looking at a calm lake's surface, only to realize it's actually seething with microscopic bubbles too small to see individually, yet collectively changing how light dances across it. That's the essence of the quantum foam signature, a potential smoking gun for the most elusive theory in physics, quantum gravity. The idea of quantum foam isn't new. Theorists have long speculated that at unimaginably small scales, space-time might not be smooth but chaotic, a seething sea of virtual particles and wormholes blinking in and out of existence. These fluctuations would be vanishingly brief, lasting mere fractions of a second, and absurdly tiny, trillions of times smaller than an atom. Yet here's the twist: certain observations of distant quasars suggest this quantum turmoil might leave fingerprints on cosmic scales. As light from these blazing objects travels billions of light years to reach us, the most energetic photons appear to arrive slightly out of sync with their lower energy counterparts. It's as if the high-energy light hit microscopic speed bumps along the way, while the rest sailed smoothly. What could cause such a discrepancy? One tantalizing explanation is that spacetime's quantum foam, normally invisible, might subtly scatter the highest energy photons, like a sieve with holes too small for sand but just right for pebbles. If true, this would mean the universe's fabric isn't just warped by gravity. It's inherently grainy, a cosmic version of pixelation hidden in plain sight. The implications are staggering. Quantum gravity, the holy grail of theoretical physics, seeks to unite Einstein's relativity with quantum mechanics, two frameworks that have stubbornly refused to mesh for a century. This anomaly could be the first hard evidence that they're not just compatible but deeply intertwined, with spacetime itself obeying quantum rules, but not everyone's convinced. Skeptics argue that alternative explanations like intergalactic magnetic fields or exotic plasma effects could mimic the same photon delays. The real challenge lies in the scale. Quantum foam's bubbles are predicted to be vanishingly small, around 10 to the power of -35 meters. For their effects to cascade up to observable cosmic distances would require mechanisms we've barely begun to imagine. Some theorists propose that under extreme conditions like near a black hole's event horizon or during the universe's first moments, quantum foam might inflate, its fluctuations magnified like shadows on a cave wall. Others wonder if we're seeing evidence of extra dimensions, where foam-like structures in higher realms bleed into our perception as subtle delays. The most profound implication isn't just about gravity, it's about the nature of reality itself. If spacetime has texture, even at scales we can't directly perceive, it suggests the universe might be built on a foundation of chaos, with order emerging only at the levels we're accustomed to observing. Think of it like zooming in on a digital image. From afar, it looks smooth, but pixel by pixel, it's a mosaic of discrete fragments. Quantum foam could be those pixels, the universe's underlying resolution finally revealing itself in the faint lag of distant starlight. Detecting this signature wasn't just a matter of better telescopes, it required rethinking how we observe the cosmos. By comparing the arrival times of gamma rays across vast distances, astronomers turned the universe into a colossal physics lab, with light itself as the probe. Future missions, like the proposed Gamma Ray Astronomy International Observatory, could settle the debate by analyzing thousands more quasars, searching for patterns that rule out mundane explanations. A confirmed detection wouldn't just earn someone a Nobel Prize, it would rewrite our understanding of existence, proving that even the void between stars is alive with quantum turbulence. Yet the biggest question remains unanswered. If spacetime foams, what stirs it? Is it the ceaseless creation and annihilation of virtual particles, as quantum theory suggests? Or something even stranger, a deeper layer of reality where causality flickers and geometry fluctuates? The quantum foam signature doesn't just hint at new physics. It opens a door to a universe far wilder than we've dared to imagine, where the smooth canvas of spacetime is actually a stormy quantum sea, and every ray of light that reaches us has surfed its waves. What if everything you see, every star, galaxy, and even the space between them, is just a projection, like a cosmic mirage? This isn't science fiction. It's the startling premise behind the holographic universe glitch, a series of bizarre correlations in cosmic data that suggest reality might be nothing more than an illusion. The idea sounds absurd, but the evidence is mounting. Imagine the universe as a movie screen, where the three-dimensional world we experience is actually encoded on a two-dimensional surface at the edge of everything. Every event, every particle, every law of physics just pixels in a grand cosmic hologram. The first hints of this glitch appeared in the way black holes behave. According to quantum mechanics, information can never be destroyed, yet black holes seem to erase it when they swallow matter. But in the 1990s, physicist Leonard Susskind proposed a radical solution. the information isn't lost, it's smeared across the black hole's event horizon like ink on a stretched balloon. Later, researchers realized this might not just apply to black holes. The entire universe could work the same way, with all the complexity of three-dimensional space encoded on a distant, two-dimensional boundary. It's like realizing the movie you're watching isn't actually happening inside the screen, it's being projected from the edges. Then came the smoking gun. Detailed studies of the cosmic microwave background, the afterglow of the Big Bang, revealed strange statistical anomalies. Certain patterns in the data matched predictions made by holographic theory, as if the universe's underlying code had left fingerprints in its oldest light. Even more bizarre, calculations showed that the maximum amount of information any region of space can contain doesn't scale with its volume, as you'd expect, but with its surface area. It's like discovering your hard drive storage doesn't depend on how thick it is, but only on the size of its label. But how could a flat surface simulate a three-dimensional world? Think of a credit card hologram tilted, and the image seems to move in 3 dimensions, even though it's just light interacting with microscopic grooves on a flat sticker. In the holographic universe, the grooves are unimaginably tiny Planck-scale pixels on the cosmic boundary, and their interactions create the illusion of depth, time, and even gravity. Even stranger, this might explain why quantum particles can be entangled across vast distances, because on the 2D surface, they're actually neighbors, like 2 dots drawn side by side on a piece of paper. The implications are staggering. If the holographic principle is true, it means reality is fundamentally informational. The universe isn't made of matter and energy as much as it's made of bits, cosmic ones and zeros etched onto the fabric of spacetime. It would also mean that black holes aren't just cosmic vacuums. They're the universe's most efficient hard drives, packing information into the smallest possible space. And if the boundary encodes everything, then free will, consciousness, even time itself might just be emergent properties of this grand projection. Critics argue that the holographic principle is still speculative, a mathematical curiosity without direct proof. But supporters counter that the anomalies in the cosmic microwave background are too precise to ignore. Future experiments, like ultra-sensitive gravitational wave detectors or quantum computers simulating holographic universes, could tip the scales. Either way, the mere possibility forces us to confront a mind-bending truth. The universe might not just contain mysteries, it might be one. A vast, shimmering illusion, flickering into existence 1 pixel at a time. The universe has a way of preserving its most profound secrets, sometimes in the faintest whispers echoing across billions of years. Among all the anomalies we've explored, none is more tantalizing than the Big Bang echo, a ghostly signal repeating at intervals so precise, it seems to pulse with the primordial rhythm of creation itself. Unlike ordinary cosmic background noise, this echo carries a pattern too deliberate to dismiss as random static. It's as if the universe left behind a voicemail from its birth, and we're only now learning how to listen. What makes this echo so extraordinary is its potential origin. The Big Bang wasn't just an explosion, it was the violent unfurling of space-time, a cataclysm so immense its afterglow still bathes the cosmos in microwave radiation. But buried within that glow, researchers detected something unexpected, a faint, repeating oscillation, like a heartbeat fading into the void. The timing of these pulses aligns eerily with theoretical models of the universe's first moments, when spacetime itself might have vibrated like a struck gong, sending shockwaves through the newborn cosmos. How could an echo survive for nearly 14 billion years? The answer might lie in the fabric of reality. Some theories suggest the early universe was a seething quantum foam, where space-time bubbles formed and collapsed in rapid succession. If one of those bubbles, a pocket of false vacuum, collapsed in just the right way, it could have produced a gravitational ripple so persistent it never fully dissipated. Picture dropping a pebble into a pond, only for the ripples to keep circling indefinitely, growing fainter but never vanishing. That's the scale of longevity we're dealing with, a vibration etched into the universe's DNA. Then there's the haunting implication of repetition. Echoes don't just happen, they require boundaries to reflect off of. So what, in the vast expanse of nothingness, could have bounced this signal back to us? One radical idea points to the shape of the universe itself. If space-time is curved into a closed loop, like the surface of an unimaginably large balloon, the echo might be a relic wave that has circumnavigated the cosmos multiple times, growing dimmer with each pass. It's the cosmic equivalent of a whisper traveling around a circular room, returning to the listener's ears long after the speaker has gone silent. But the most electrifying possibility is that this echo isn't just a relic, it's a key. The precise frequency of the pulses could encode information about the universe's initial conditions, the exact balance of matter and antimatter, the strength of fundamental forces at the moment of creation, even clues about what, if anything, came before the Big Bang. Decoding it would be like uncovering the universe's birth certificate, written in a language we're only beginning to understand, yet skepticism lingers. Could this just be an artifact of interstellar interference or a quirk in our detection methods? The signal is so faint that distinguishing it from noise pushes our instruments to their limits. Future observatories, like the next-generation space telescopes designed to map the cosmic microwave background in unprecedented detail, might finally settle the debate. Until then, the Big Bang echo remains a tantalizing maybe, a shadow on the cave wall of cosmology, hinting at truths we've yet to fully grasp. If confirmed, this echo wouldn't just rewrite astronomy textbooks, it would redefine our connection to the cosmos. We'd no longer be passive observers of a distant past but active listeners to the universe's first cry, a sound reverberating through time itself. And if the birth of everything left traces we can still detect, what other messages might be hidden in the static, waiting for us to tune in? The echo doesn't just offer answers, it invites us to ask questions we've never dared to voice. These 28 cosmic anomalies aren't mere footnotes in astronomy's grand narrative. They're flashing warning signs that our map of reality is missing entire continents of understanding. Each one, from the time-frozen galaxy to the whispering quantum foam, acts like a crack in the foundation of modern cosmology, revealing glimpses of a far stranger universe lurking beneath our textbooks. The phantom expansions, the gravity-defying flows, the echoing silence where cosmic noise should be, they all point to a cosmos that plays by rules we're only beginning to glimpse. Consider what's at stake here. For centuries, we've built our cosmic models on assumptions of uniformity, that gravity behaves the same everywhere, that dark energy exerts steady pressure, that space-time stretches smoothly. But these forgotten events scream otherwise. They paint a picture of a capricious universe where the fundamental forces might have dials we can't see, turned to different settings in hidden corners of reality. It's as if we've been studying a vast, intricate machine by only examining one gear, unaware that the rest operate on entirely different principles, the most humbling realization. We're likely seeing just the tip of the iceberg. If 28 universe-bending anomalies have already slipped through the cracks of mainstream cosmology, how many more remain unnoticed? Every time we build a more powerful telescope or develop a more sensitive detector, we peel back another layer of cosmic mystery. The James Webb Space Telescope's recent discoveries, galaxies too old to exist, structures too large to form, are already adding new entries to this growing catalogue of cosmological contradictions. This isn't just academic curiosity. Rewriting cosmic history has real consequences. Our understanding of dark energy, the force accelerating the universe's expansion, directly affects predictions about the ultimate fate of everything. If dark energy can spike or fluctuate, as some anomalies suggest, the cosmos might not end in the slow heat death we've predicted, but in something far more dramatic or far stranger. Even time itself, that most fundamental river, might not flow uniformly, with some regions of the universe locked in different tempos like pockets of a vast, discordant symphony. What ties these anomalies together is their refusal to fit neatly into existing paradigms. They're not just gaps in our knowledge, they're fractures in the framework itself. Like explorers finding compass needles spinning wildly near some unseen magnetic pole, we're being shown that the universe's true north may lie in directions we haven't even conceived. The frozen galaxy challenges our notions of time's flow. The invisible supercluster rewrites the rules of cosmic structure. The holographic glitches hint that reality itself might be a shadow play on dimensions beyond our perception. Yet within this uncertainty lies science's greatest opportunity. Every cosmic rule breaker is a potential doorway to deeper understanding, a chance to glimpse the universe's hidden blueprints. The anomalies that frustrate today's models might become the cornerstones of tomorrow's breakthroughs, just as quantum mechanics arose from the ashes of classical physics failures. Our task isn't to force these puzzles into existing boxes, but to let them smash the boxes entirely and build new ones from the pieces. So where do we go from here? The path forward requires equal parts humility and audacity. Humility to admit how much we don't know, and audacity to imagine explanations that might seem ludicrous by today's standards. We'll need telescopes that peer deeper, detectors that listen more keenly, and theories bold enough to accommodate a universe far wilder than Einstein ever dreamed. Most importantly, we'll need to keep that childlike wonder alive, the willingness to be astonished when the cosmos reveals yet another card from its bottomless deck of surprises. The cosmic story isn't just being revised, it's being reinvented before our eyes. With each anomaly uncovered, we're not just filling in blanks, we're discovering that the page we're writing on is bigger, stranger, and more magnificent than we ever suspected. So keep looking up, stay dazzled by the mysteries, and remember, the universe's greatest revelations often come disguised as its most confounding puzzles. Our journey to understand reality has only just begun, and the next cosmic revelation could be waiting in the very next photon that reaches our detectors. The adventure continues.